So we'll begin chapter 9, gas power cycles. Now I've broken this chapter into several lectures, trying to keep the lectures down to within 15-20 minutes or so. So first of all, let's look back and remember the Carnot cycle. That's the idealized cycle. The Carnot cycle is based on 4 totally reversible processes. You have, for example, the um, isothermal heat addition. Let me get a highlighter here, and I'll try to um, highlight this for us as I go through this. So you have the isothermal heat addition occurring at a constant temperature, TH. You have an isentropic expansion from 2 to 3. You have an isothermal heat rejection from 3 to 4. And then you uh, have an isentropic compression back from 4 to 1. So the fluid follows this complete cycle over and over and over. It's repetitive. Now, if you look at that diagram on a temperature versus entropy diagram, again, we've looked at this before. It's a rectangle. So from 1 to 2, you have heat being added to the system, and from 3 to 4, you have heat being exhausted to the system. So this Carnot cycle operates between 2 temperatures: a uh, heat sink temperature (TL) and a heat source temperature (TH). So we went through and we calculated the efficiency of the Carnot engine, 1 minus TL over TH, and this is the best you can do, obviously. Um, the Carnot cycle. Now, why don't we build Carnot engines? Because they're really sort of like a theoretical model. It would be very costly, expensive, and not practical to build a Carnot cycle. So in real systems, how does real systems differ from the Carnot cycle? Well, their efficiency is not as high, obviously. And also, if you look at like a PV diagram of an actual cycle, which is the highlighted red here, you can see it's actually pretty complicated. And this is a simplified um, actual cycle, really. So they're sort of simplified. So as a first attempt at this, what we want to try to do is we want to come up with what's called an ideal cycle. We want to come up with something that models the actual cycle, that's close to it as possible, and that we don't strip out all the physics of it, but not make it so complex that we can't deal with it. So that's the whole idea between an ideal cycle um, and a real and an actual cycle. And of course, reversible cycles such as the Carnot cycle always have the highest thermal efficiency. Unlike real cycles, they're totally reversible and unsuitable as a realistic model. That's why we don't use them. We can't really build Carnot engines. So how can we simplify um, a cycle but still retain uh, most of the elements of the real cycle? That's what we're going to look at here in the next couple of slides. So how does we also looked at how uh, efficiency of a heat engine compared to it is different than the efficiency of a Carnot cycle. We were able to calculate that the efficiency of a heat engine is determined by how much the work output divided by the heat input. So how we simplify this? Well, for a gas power cycle, remember this is the working fluid is a gas here. So if you look at like typically in that case, you have a combustion chamber. Let's imagine, for example, the uh, gasoline uh, auto cycle. You know, it's very pretty complicated what's going on in the combustion chamber. You have air coming in, you have fuel coming in, they mix, the spark hits it, and then the piston goes up and down, obviously, and then the exhaust products are expelled. Well, what we're going to do is we're going to simplify this actual model with the following assumptions. We're just going to look at like air coming in, heat coming in. You have a heating section, and you just pump out air. So here in our system, what we're going to look at is what's called the air standard assumptions. We're going to assume that air is the working fluid, and it circulates continuously in the closed loop and always behaves as an ideal gas. Now we know that's not true. Air in certain situations doesn't behave like an ideal gas, but As a first approximation, we're going to look at it as being an ideal gas. We're going to look at all the processes that make up the cycle as internally reversible. We're going to say the combustion process is replaced by a heat addition process from an external source. And we're going to treat the exhaust process as replaced by a heat rejection process that restores the working fluid back to its initial state. So these are the assumptions we're going to make to simplify the model. There's also what's called the cold air standard assumption, where the working fluid is considered to be air with a constant specific heat at room temperature. We're also going to use that one. So what's referred to as the air standard cycle is a cycle for which the air standard assumptions are applicable. All of these guys are here. So what this does is it simplifies our model, and so we can get a first good approximation of what's going on, but you still get results that are usable. Let's look at a quick overview of reciprocating engines. First, there's two basic types. There's a spark ignition engine, such as the gasoline engine, and there's a compression ignition engine, such as the diesel engine. In both cases, you have the cylinder with a piston traveling up and down inside of the cylinder. The maximum distance downward the piston can travel is referred to as bottom dead center. The furthest upward the piston can travel in this particular diagram is referred to as top dead center. So the difference between bottom dead center and top dead center is referred to as the stroke. It's the length of travel of the piston inside the cylinder walls. So let's look at the working fluid. So when the piston is at bottom dead center, you have a maximum volume inside the cylinder wall. And as the piston moves upward toward top dead center, the working fluid gets compressed into a very small volume. So here we refer to the compression ratio as the ratio of the maximum volume to the minimum volume. And what we want to be able to do is be able to calculate how much work we can get out of this cycle. So let me switch over to the pointer and I'll show you what we can get out of the pen. We'll see what we can get to some of the equations we're going to need. So first of all, work, if you remember back from your university physics, is defined to be a force change in displacement. Pressure is equal to force divided by area. Now the change in displacement, the delta y here, that's the stroke distance. The pressure is the pressure inside the cylinder wall. So here we can solve this equation for force simply equals pressure times area, and we can plug it back in the first equation, and we can write work equals pressure times area times the delta y. Now, let me switch back to the laser pointer here. Now here, the pressure inside the cylinder wall is obviously going to vary. It's not a constant. It's going to be a minimum when the piston is at bottom dead center. It's going to be a maximum when the piston's at top dead center. But what we can do is we can solve for sort of like an average mean effective average pressure. So we take this last equation, we solve it for pressure. We get work divided by the difference in volume. Because here you have A times delta Y, that's a volume. A is the piston area, and Y is the stroke. So the delta Y is going to be A times the bottom dead center minus the top dead center. So this just defines what's called a mean effective pressure. That's the average pressure inside the cylinder wall. So here, the work net, we can write it as mean effective pressure times the piston area times the stroke, or mean effective pressure times the displacement volume. So let's plot this out on a pressure versus volume diagram. So the actual cycle looks like the following curve. It's actually a pretty complicated kind of shape, but the net work is the area inside the diagram. Now this is exactly equal to the area of inside the little triangle here if we've defined the mean effective pressure like we did in the previous slide. So you can see how this greatly simplifies the analysis, because it's easier to calculate the area of a rectangle than it is an area of a complicated shape. So this shows the piston traveling between bottom dead center and top dead center.